Okay, Assalamualaikum and good morning, everyone. So today we continue with I think chapter 5, and then we will see we can finish chapter 5 today because some of the examples here are important for us to understand things. So let me go to the whiteboard. So here's an example. Okay, again we are still doing multiple integrals. Okay, and here's an example of the cone. Okay, given by this figure, and then essentially these are considered a solid. So it's not just the surface. So there is some material inside, and then we are supposed to find the z coordinate of. So there are two problems. Z coordinate of centroid, and then another one is the moment of inertia of solid when rotated about the axis of the cone. Axis with respect to axis of the cone. Okay. So the first thing is again, remember how we define centroid is to look at essentially the equation of center of mass. So probably we want to do that first. Look at the mass of the cone itself, and because later on when we do moment of inertia, we will have to express in terms of the mass, the usual way of doing things, and then yeah, okay, and we should start by looking at okay what coordinates that we are going to use. Of course, naturally, if you look at this particular, okay, the natural coordinates is going to be your cylindrical coordinate, because essentially you have your z-axis to be playing the role of where the height of material inside the cone until its height h. H is a constant given here. That's where the end of the cone is supposed to be. So the radius over here, for example, will be your z coordinate. Okay. So in other words, over here, one should be writing. Okay, first of all, it's the cylindrical coordinate because you need your z. Okay, and then because the circular sort of cross section of the cone, then you probably need r, theta, and z. Okay, so here your r will be your z coordinate. Okay, so let's consider what is the mass element in this particular case. The mass element, usually denoted as dm, will be given by the density times the volume element. Okay, and the volume element is now no, originally it should be the dx dy dz, but since you're using cylindrical coordinate, so you're going to have instead of dx dy dz, we'll be having it as rho times r dr d theta dz. Okay, so your r here is essentially coming from your Jacobian. Okay, going from your Cartesian coordinates to your cylindrical coordinates, you have a Jacobian which is not equals to 1, so you have to include that. Okay, so let's now try to integrate this. So you get your mass m equals to rho dv. Okay, then your rho is considered as constant in this particular case, so I can bring it outside. So it will be integral of dv, which is coming from that volume element here. So that, let me just put all the integrals first. So you have your dz, your dr, and then under the from the Jacobian we have to put r here, and then here we have theta. So let's look at what are the limits for this. Well, for theta it's obvious, it's the planar part. Okay, this is x and y here. So your theta is going from 0 to 2 pi, okay? So here is 0 to 2 pi. The r, okay, what's the limit of that? That will go from 0 to z, okay, because that depends on this picture. So depending on where the point z is, that will be the giving you the radius over here. Okay. And then your dz, of course, is going to go from the bottom part here until this part, okay, where it is the flat part of the cone. Oops. So let's do that. So this is h. So the easiest integral we do first, so that gives you 2 pi, and then you have the r, that will give you half r squared. So let me do this, z, and then half r squared integrated from 0 to z, and that will give 2 pi, that will be 1/2. So let's bring out half in front. So integral of the z of z squared from 0 to h. So finally we do the integration. It's a simple enough integration there. That will give you, oh, I've forgotten the rho. Rho should be here. So pi rho h cubed over 3. Okay. So later on we probably need, so in other words, m here is going to be equals to that. So later on we'll need to use m inside your what you call moment of inertia. So let's re-express your rho here in terms of m. Okay, this is for future use. Okay. And then we will now proceed. Oh, the other thing, okay. So from over here, you could also see that, okay, since rho is constant, this is actually integral of the volume element. So from there, you can also get v, integral of so-called dz, the r, the theta times r there. Okay, so there's a triple integral here. So and then from the calculation is just the same thing, the same calculation, so without the rho there. So that will give you pi h cubed over 3. Okay. Right. So now let's go to the centroid. So that's the question that is asked for. The centroid, okay, essentially given by this integral z bar. Remember that I should have mentioned that what we want is just the z coordinate of the centroid. I'm losing my cursor. Because that is the if you think what the coordinate of centroid in terms of x and y, what would be your guess? Anyone? So essentially here, let me just write that. It's obvious that x bar and y bar is going to be equal to 0. Okay, because it's symmetric about this particular axis. Okay, so the centroid has to be along that particular axis. So that's why we only are interested. Oops. We are only interested in getting the centroid coordinate of z. Okay, so here, so we have from previous, this equals to the integral of z bar dv equals to z dv, and we have done z bar here is going to be constant, so basically that gives you z bar outside, and then integral dv is we have already calculated above, v equals to pi h cubed on 3. And then the integral of this will have, you have to integrate it. Okay, so let us do that. So this is dz going from 0 to h, and then we have your r going from 0 to z. Oops, I should mention, let me undo that for a while. Under z, there's only the z is going to appear from there, so that gives you z here. So integral of r 0 to z, this is in this particular case you have to have that dr and r there, and then finally your theta. Okay, again this is almost the same integration apart from this part. Okay, so let's just do the integration, and you'll find out that the first two is just something that we have done before. So what's left is essentially the z integration is half z cubed there from 0 to h, and that gives us pi h to the 4th over 4. Okay, the 2 here is cancelled off. Oops, why is that happening? H to the 4th over 4. Okay, so now you just simply calculate your z bar. Therefore, z bar is going to be pi h to the 4th over 4. Bring this factor on the other side, that gives you 3 on pi h bar, sorry, pi h cubed. and that gives you 3/4 each. And let's make sense of this answer. No, this is one thing one should have a feeling for. If you look at where the centroid should be along the z-axis, you can almost think of what's going to happen is that because there are more mass at the top compared to the mass at the bottom here, so it will be more towards the upper part, and that is precisely what you get, is that your z coordinate of the centroid is 3/4 arc no above, okay, of the height. Okay, that makes sense. So next is to do the moment of inertia. So let's remember what's the moment of inertia about the axis of the cone. So let's just go back to the cone here. Oops, what am I doing? Thing one is, let me do this bit by bit. Where's my cursor? Okay, so what is axis of the cone? Axis of the cone is simply your z-axis. So in other words, what is the perpendicular distance over here? The perpendicular distance, let me do this in red. Perpendicular distance over here will be your x squared plus y squared. Okay. So I'm not sure whether this is actually visible. So depending on where precisely on the, if it's over here, then your y coordinate will be sort of your x coordinate will be 0 and things like that. So it depends on where the x and y along this particular cone. Okay, but essentially that is your perpendicular distance, x squared plus y squared. So let's do that. So moment of inertia is given by I equals to, usually we have the rho inside, but now the rho is constant, so we have this instead. So z equals to 0 h dz, and then remember that your perpendicular distance is x squared plus y squared, and that's equals to r squared. Okay, so in other words, your r squared will appear under the dr integral. So this is from 0 to z dr, and then you have your Jacobian here, and then you have your r squared, which is your perpendicular distance. And finally your theta, which is a trivial integral to do. Okay, so let's just jump into the z integral. So that gives you rho times 2 pi, and then dz is, it has to take from this is r cubed, so that will be 1/4 r/4 related from 0 to z here, this 0 to h, so that gives you so I will have to have just hang on a minute, yeah, pi rho over 10 where's the 10 coming from? This is 2, this is factor of 2 here, and then when you integrate z to the fourth, you get 1 over 5th, so you get 5 times 2 at the bottom. So pi rho over 10 h to the 5th. Okay, so this is essentially your moment of inertia at about the z-axis. But remember, what we need to do is to rewrite your moment of inertia in terms of your m. I already given you what m is, what rho is in terms of m. Okay, so we have a rho here. So let's recall what that is. Rho equals to 3 m over pi h squared. Okay. So we have pi over 10. Rho is what was it? Okay, 3 over pi h squared times m, then times h to the 5th. And that gives you 3 over 10 mh cubed. Something is wrong. Let me see what was the h cube is not h square. Let me erase that. This is h cube, so then you have h squared. Okay, so that is an example where if you look at it, it's probably looks a little bit complicated because it's a inverted cone kind of thing, but if you choose your coordinates correctly, in this case it's your cylindrical coordinates, then things can get easier. I would like to do another example. There's another example of the sphere, which I will not do it here. I will jump straight to another example given in the book, which is the case of the ellipsoid. And once we have this example, we will actually finish off. Oh, that's another section. Okay, let me do that. Okay, so moment of inertia about z-axis of solid ellipsoid. And that is given by x squared a squared plus y squared over b squared plus z squared over c squared equals to 1. So like before, it's convenient for us to consider generally what is your mass. In this case, it's given by rho dx dy dz. We have not figured out what coordinates to use, but let's just write the easiest one, which is your Cartesian coordinate, and then another one will be your I. So your I, again, about the z-axis, this will have to be integral of rho. Rho is constant, I've forgotten to mention that. So you can bring outside. And then your perpendicular distance about the z-axis is x squared plus y squared, just like before. Okay, so now how do you do the integral in this particular case? Well, again, the fact that this is not really symmetric because you have all these different values of a squared, b squared, c squared. at the denominators, what one can do is to do a coordinate transformation. Coordinate transform them into rescale them as follows. So you have x equals to a x dash, y equals to b y dash, c equals to z equals to c z dash. Okay, and then of course the differential will be just a dx dash, b dy dash, and then dz or dz is c dz dash. So I'm just going to replace your dx dy dz on both parts here. So that will actually give us the following. So let's take the case of your mass first. Your mass will be given, rho is constant, so we can bring it outside. And then because of the dx dy dz here, okay, then I will have the factors a, b, and c outside. And then you have the integral of dx dash dy dash dz dash. Now here what one can also do is the following. Okay, how do we integrate this? Well, first of all, if you look at the earlier equation over here and replace by the new variable, then what you're going to get, this is going to be x dash square plus y dash square plus z dash square equals to 1. And this is essentially equation of a sphere or ball, okay, if you consider the thing inside as well. Okay, so the volume of a sphere, this will now give you the volume of sphere. Okay, so and we know that, so we can do the calculation if we want, but we know that from past experience, your volume of your sphere is going to be 4/3 pi r cubed, and your r over here equals to 1, so you get that. Okay, so that we have not really done the integral because we are using the standard formula for volume of the sphere. But for the moment of inertia, you can see that that's going to be a problem. Okay, so let's write down the moment of inertia in the new variables. So that is going to be rho ABC, and then the triple integral of a squared x dash squared plus b squared y dash squared, and then dv dash. So this is actually, let me just erase that a little bit. Oops. So this is volume element of a sphere, which is dv dash. Okay, so this whole thing is dv dash. So now how do we integrate this? Well, for a sphere, trying to draw a diagram here. For a sphere, you know that it's going to be symmetric in all directions. Let's draw that. So essentially a sphere, sort of symmetrical, but no, in all directions. So in other words, I should be able to write the following. So for example, this one, let me just take this particular case, and then ignore your e squared there. So let's consider, for example, triple integral of x dash squared dv because of the symmetrical shape of the sphere. This should be also equals to y dash squared dv, and also same as z dash squared dv. Okay, because they are just symmetric about this exchange, interchange of x, y, z. Okay, so what one can do now is to essentially, all right, if I have that, then I can write the following: integral of, say, r dash square dv, and r dash square is essentially equals to x dash squared plus y dash square plus z dash square plus sorry, I have a visitor. So then because these are all the same with respect to the integral with respect to dv, then I can write the following: or in other words, what do we have? The integral, sorry about my horrible handwriting, the integral x dash squared dv is going to be equals to 1/3 of integral of r dash squared dv. Oh, sorry, this is all dv dash under the new coordinate system. And let's do the integral now. So the integral, remember, dv dash is supposed to give you the polar, what you call, written in terms of the polar coordinates or spherical polar coordinates. So that will give you r dash square sine theta dash dr dash d theta dash d phi dash. Okay, remember this is essentially your dx dash dy dash z dash, and this factor essentially is your Jacobian. So now we can do the integral. Okay, so the integral, let me just try to jump ahead a little bit. So the integral of, since there's only r dash square in this integral, so we'll do the r dash later on, but for d theta dash and d phi dash, it should be clear to you that gives you 4 pi. Okay, you can do this. So the integral of say theta, for example, is going from 0 to pi theta dash sine theta dash. Okay, and then integral of phi dash is from 0 to 2 pi. So you do that, and then this thing will be equals to 4 pi. Okay, so you get 4 pi over 3, and then what's left is the integral of r. So the r is going to go from 0 to 1. You remember your equation of the sphere is essentially that. So r equals to 1. And then remember you also have the Jacobian factor here, r squared, and also you have your r squared over here, so that's r dash to the fourth. So this is r dash. Okay, so finally if you write it down, that gives you 4 pi let me just check what they do. Okay, let me just write what I have over here first. It's 4 pi over 15. Why is there a 15 there? Is because you have that 1/3 thing. Okay, so going back to your moment of inertia here, so this is equals to a squared integral of x dash square dv dash plus integral of y dash square dv dash. There's supposed to be a b squared also. Okay, this already we have there. It's going to be 4 pi over 15. Oops, I hope I get the right answer. Yeah, so this is rho A B C of 4 pi over 15 times a squared plus b squared. Okay, 4 pi on 15 is coming from the integral, and then you still have your a squared and b squared here. So now remember, we want to re-express your moment of inertia in terms of your mass. So earlier we have already done that. Your mass is given by rho ABC for 1/3 pi. So let's try to remember that. So rho ABC for 1/3 pi, but here you have a 1 over 15, 4 over 15. So I can rewrite this as follows. So for 1/3 pi times 1 over 5 a squared plus b squared, and this is now your m. So basically what I have is 1 over 5 m a squared plus b squared. So that gives you the answer. So again, the thing that you need to understand is essentially the trick using the change of coordinates. Okay. And then the other thing is to make sure that you have your Jacobian, okay, when you do polar coordinates. And then the other thing that you probably need to understand is to determine the integral limits. Okay? So these are key things that you should know. I hope everyone's getting in. Okay, so let me do one last part of this chapter. It's also important, but somehow this is a bit odd because it's sort of use vector calculus, which is going to be introduced in chapter 6. But since it's in chapter 5, I'm going to just do it anyway. So the thing that we want to do is essentially a surface integral. So let me just try to give you a picture first. Go down. So what we need is this picture. So let me cut and paste that. So over here, what's the problem is, normally what one does is to have a rectangular area element given by dx dy. Okay, so this is a normal flat surface. But in some circumstances, we are forced to find the area element which is on a curved surface. On curved surface, then we need to somehow relate your flat surface area element with the curved surface element. So what one does is a kind of projection over here is down here, essentially your, let me just see, over here is, never mind, I'll just say dA1 here, and then this is the area element over here that we need is dA here. Okay, so how do you project that? That depends on the surface over here, and also what characterizes that surface is going to be your normal vector. Okay, so we need to somehow relate to that normal vector. Okay, and let's suppose we know the angle over here between the normal vector and this is the z-axis. Let me just properly, so in other words, let me draw here. Here's your normal here. No, I get the wrong, sorry, I got the wrong thing way around. Okay, let me do, okay. The normal is like that. Okay. And this essentially is the unit vector along z direction. Okay, so if you know the angle between this, so that is say gamma, then we have this kind of projection. The x dy will be given by dA cos gamma. Okay, this needs a little bit of geometry, you know. So you sort of have this angle over here, and then your flat is flat. So here's your normal here. So when you project it down over here, then you get your cos gamma. So here, then one can write your dA to be equals to 1 over cos gamma dx dy, and then this is just your secant. Okay. So in order for us to sort of do the calculation for the area surface integral, okay, along that, so what we need is going to be the integral dA equals to, since this is going to be if you can actually express it in terms of a meaningful variable, then it's okay, but otherwise you need to do this. And this cos gamma, let me just write down, your cos gamma is coming from normal dot k. So our problem here is now trying to establish what this angle gamma is, okay? And later on in vector calculus, one should be able to show that given a surface, say, phi, which is a function of x, y, z here, equals to constant, so that defines the surface, then your gradient of phi, or sometimes it's in terms of notation, it's given by that del operator, I d phi dx plus j d phi dy. So here is encroaching the area of vector calculus here, which is the subject of the next chapter. We can do it here. Okay. So this is already well, it's parallel to the normal of the surface. Okay. So what do we have over here? Then we can really write your normal to be the gradient of your phi divided by its magnitude. So you get a unit vector for n. Okay. So then you have your n dot k, which is equals to n k cos gamma, okay, equals to here is going to be magnitude 1, this is also magnitude 1, and cos gamma what am I doing? So from, okay, this is right. N dot k will now be given as del phi dot k divided by del phi. But del phi dot k is essentially d phi dz. Okay. So in other words, we now have a way of determining what your gamma is through your normal. And your secant gamma in this particular case will then just be square root of, this is your del phi here, gradient phi, square plus u phi y square plus phi z square dy by d phi dz. Okay. So this on top here is essentially your modulus of gradient phi. Okay, so that is your secant gamma. So let me just if one has the surface, okay, just a special case, yeah, I want an example here because that should be the thing that should be of interest here. So here your phi x, y, z will simply equals to z minus f of x, y. Okay. So and then over here, then you have your d phi dz equals to 1. Okay. So in other words, your secant gamma in this particular case, secant gamma will be square root of the f dx square plus the f dy square, and then your d phi dz is just simply equals to 1. So if it's this particular case, then you can just simply use this. Okay. So let us do one example before we go. Hopefully I can finish this. I need to do this so that you can actually see what's going on. So let me capture that. So here's an example of area cut from upper half of sphere which is given by x squared plus y squared plus z squared equals to 1, okay, by the cylinder x squared plus y squared minus y equals 0. So let me just push this thing up and copy paste here. So over here, this is what the picture is supposed to be. So your cylinder is cutting. So this is say the sphere, and this is the cylinder. Now this cylinder, the cross section of the cylinder is given by a circle here, x squared plus y minus a half square plus, sorry, doesn't have a plus there. So y plus a half, sorry, y minus a half into z. Sorry about this. Y minus a half square. So this is half here. And then this radius would be a quarter. 1 on 2 squared. Okay. So if you expand this, then you get that equation there. Okay. So how to do this? Essentially, the surface that you want to look at is the cut version of that sphere. So your sphere is now giving you phi x squared plus y squared plus z squared equals to 1 is the constant. So in other words, if you take the secant gamma, will be del phi over d phi dz, and that gives us a square root of 2x squared plus 2y squared plus 2z squared over 2z. Okay. Now x squared plus y squared plus z squared is going to be equals to 1. So that you have 4 times 1 divided by 2z. Sorry, not 4. So when we take the square root, it will be 2. Sorry. So let me erase that thing off. So this is 2. So in other words, your secant gamma is 1 over z. Please don't. So this is called 1 over z. So we can now integrate that. So let me just try to finish this off. Oh dear, come on. So A is now given by your secant gamma, which is 1 over z of dx dy. So our problem now is to determine what are the limits. Okay, so the limits is going to be y equals 0 to y equals to 1. Okay, which is this limits over here. And then the other limit is for the x. So the x is going from here to here. In other words, to this curve over here. And we also have this part. So there are two parts which is symmetric. So we only need to do one of them. So in other words, the area will be the following. This is equals to 2. 2 is coming from the two parts of that. Integral of y equals 0 to 1 of dy, and then what's the curve of this? The curve of that will be x equals 0 to square root y minus y squared. This is from the equation of cylinder dx over 1 minus x squared minus y squared. Okay, so this is coming from your this whole thing is coming from there. Okay, so I will trust you to be able to read what's next is to convert this into a polar coordinate and then do the integration. So so there are a few things that one needs to be able to do is to be able to make sure what are the right coordinates to describe the area of the surface over here, and then using the equation of the surface, then find your secant gamma. So the rest you can actually read the rest. So I'll stop here for today. Okay, so the next lecture will be on your chapter 6. Okay, so that's it. Let me go to you and download your attendance. We still have another week, right? So I'm pretty sure I'm not able to cover this with your face-to-face this virtual lectures, but I will do some recorded lectures for you to go through. Okay, that's all for today. Thank you, everyone.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.